while I didn't really expect us to still be out, here we are. So, gonna continue where we left off. Remember, you're responsible for all this material. So, not watching the video, it's not really an option. So, either way, here we go. Keep on going. So, other pollutants in the atmosphere that can contribute is methane. Methane has its own little problems. So, methane is the most abundant hydrocarbon in the air at 1.8 parts per million by volume. Now, in most situations, the larger, heavier hydrocarbons are less abundant. However, in certain urban areas, these large hydrocarbons can reach as high as 5 to 10 ppmv per unit of carbon as a result of the vehicles. So keep in mind, like 5 carbon unit would only be 1 ppmv, but per carbon. So it's like, so you multiply it by a factor of 5. If it's 8, whatever, it gets bigger. Methane only has 1. So the importance of looking at mixtures as it relates to carbon is that this oxidation process that we talked about from alkane to aldehyde can occur once per carbon in a carbon chain. So having a higher hydrocarbon count means more opportunities to oxidize. Methane only has that 1. But so though in rural areas where there's not as much traffic, we get other hydrocarbons such as terpenes and other tree-derived volatile organic carbons that I've mentioned previously. And while the hydrocarbon mixing can be relatively high, it's still something like 10 to 20 parts per billion by volume of carbon, and which is still 100 times less than the concentration of methane. Now, methane we cannot prevent because there's several natural sources as well as anthropogenic sources. Now, a big source that comes from humans is the production that during the extraction, production, and transportation of natural gas, some of it's inevitably going to leak. It's just no way to keep it perfect seal, so some of it's escaping throughout this process and generating methane in the atmosphere. However, some of this gets produced in biological reactions that occur in submerged soils. So you have a swamp, you're not necessarily in control of that. You have a rice field, well, yeah, you've generated that rice field, so it's going to happen. Or you have a landfill, it's going to be generated as things decompose in the landfill. And the big problem with methane, besides the propensity to oxidize, is it's a greenhouse gas. It means it absorbs our infrared light. Now, while all hydrocarbons have ability to react with the hydroxyl radical, the rates of oxidation vary by substance. So different chains of hydrocarbons will oxidize at different rates. Methane is in fact much slower than the other hydrocarbons. It doesn't like to oxidize as much. So its lifetime is something like 12 years. So it's more of a greenhouse gas than one that's going to be oxidized in the smog reaction. But we can still see this reaction occurring. That, remember, the hydroxyl radical pulls off a hydrogen to form a methyl radical of some kind. That methyl radical bumps into oxygen and some other compound to shake off some energy to form a peroxymethyl. The peroxymethyl can then bump into NO to form NO2 and form a alkoxy, or this would be methoxy radical. And then the methoxy radical can generate a peroxide radical and an aldehyde. This would be formaldehyde in this case. Now, this reaction is analogous for the larger hydrocarbons, but the formic acid specifically can photolyze at wavelengths of less than 330 nanometers. So it can absorb some of this high-intensity light to further radicalize. So it can split off a carbon-hydrogen bond. And that carbon-hydrogen bond produces two radicals, one of which forms another peroxy radical, and the carbon monoxide can then form more hydroxy radicals, and these hydroxy radicals can form more peroxy radicals. So the net reaction is that methane has the capacity to react with 5 oxygens and 2 waters to form 2 peroxide radicals and 6 hydroxide radicals and carbon dioxide in this process. So that's a lot of potential for smog creation. Now, as I said, it's a slower process, so it's less of an issue, but it's not something we can just neglect. So let's look at a quick calculation. So example calculation, this rates of hydrocarbon oxidation. So we're rating a generic reaction. The rate is equal to the K constant. This is what my Gen Chem 2 people are looking at right now. This is a differential rate law. Rate is equal to a reaction rate constant of the second order reaction of hydroxy radical plus the VOC. We're writing it generically because the VOC can be a variety of different hydrocarbons. And so that variety of different hydrocarbons will have a different K constant. But the VOC will also have a different concentration. So looking at it, let's compare methane and hexane. For methane, methane has a higher concentration of 1.8 ppmv. Hydroxyl radical has something like 2 times 10 to the 6th molecules per centimeter cubed. And the rate constant for methane is 8.36 times 10 to the negative 15th centimeters cubed per molecules per second. So one of the first things is we got to turn ppmv into units we can deal with. So ppmv, parts per million by volume. So we're going to convert this pressure into molecules. So 1.8 times 1 atmosphere divided by R and T is going to give us moles per liter. So we divide by 10 to the 6th to get rid of the parts per million. The moles we are multiplying by Avogadro's number to turn it into molecules. And the liters we are multiplying by the conversion of liters to centimeter cubed to get this into the same units as my hydroxyl, which is molecules per centimeter cubed. So the concentration of molecules per centimeter cube of methane is relatively high, 4.8 times 10 to the 13th power, compared to hydroxyl. So at this point, it just becomes a mathematical problem of we plugging in these 3 values, the K, the hydroxyl, and the methane, and multiplying across. We're just watching out for our units. We're just really watching out for our exponentials. So when you multiply this across, you get the rate of methane oxidation is something like 8 times 10 to the 5th molecules per centimeter cubed are reacting per second. So we'll remember this number later when we compare this. Now for hexane. Hexane is something like 100 micrograms per meter cubed. So we need to convert that into the same units. Now the hydroxyl concentration is the same, hexane rate is a little bit faster at 5.61 times 10 to the negative 12th. Let's jump back real quick. So 5.6 times 10 to the negative 12th versus 8.36 times 10 to the negative 15th. Close to 1,000 times, a little bit less, definitely less than 1,000 times faster, but getting close to there. So converting micrograms to moles. So micrograms per meter cubed. First, converting micrograms to grams. Converting meters cubed to centimeters cubed. Okay. Now the molar mass of hexane. Hexane is C6H14. So that means if I count up all the carbons and all the hydrogens, it's going to weigh something like 86 grams per mole. So I'm converting my grams of hexane to moles of hexane. Then I'm converting moles of hexane to molecules of hexane. So this is 7 times 10 to the 11th molecules per centimeter cubed. So let's look back. 7 times 10 to the 11th compared to 4.8 times 10 to the 13th. Quite a bit more concentrated with methane, but as we'll see when I plug in my three values, you get 7.9 times 10 to the 6th molecules per centimeter cubed. So even though the concentration of hexane is quite a bit less, maybe 100 times less, the rate of methane production of oxidation is something like 10 times slower. The rate of methane oxidation is about 10 times slower compared to that of hexane, just because hexane reacts that much faster. Now, however, if the hexane concentration were to drop off, as I say down there, say for example in a rural environment, the rate will drop off significantly. So in one where methane more or less stays the same and hexane drops, the rate of hexane oxidation will go down, and so methane will be the preferential oxidation. But so to summarize our volatile organic carbon oxidation, initiation of this oxidation process occurs either by a hydrogen extraction or a hydroxyl addition. So we either pull off a hydrogen or add an OH. This produces a radical capable of adding dioxygen to form some sort of peroxyl, or it's something capable of abstracting a hydrogen in the case of aromatics. Now, this peroxyl species gives off one of its oxygens to NO to form NO2, and the product then either loses a hydrogen to form a another dioxygen, or splits. But the net effect is always the formation of an aldehyde and some sort of hydroperoxyl radical. Now, from there, that aldehyde can either react with NO2 to form the PAN, the PANs, and which can undergo further oxidation by hydroxyl radical or photochemically decompose. And then these decomposition products are subjected to repeated oxidations until we finally get CO2 and water. And this is just a small cross-section of many different complex and competing reactions that occur simultaneously. But each has its own rate, each needs to be measured, and concentrations estimated in order to model the system. So we got a rough idea of what's going on, but to model this, it is a Gordian knot. It is a complex mixture of competing reactions that change concentrations here, there, and everywhere that make trying to get a correct model near impossible. We can get close, but it becomes really, really hard. Now, we're going to look about the. We're going to spend some time looking at internal combustion engines from here on. So, one of the major anthropogenic sources of VOCs and other atmospheric pollutants are from the internal combustion engine of vehicles. We can break them down into 4-stroke engines that work on gasoline or petroleum, is our most common type. We'll talk about diesel engines like buses, trucks, locomotives, ships, and some types of power generators. We'll look at 2-stroke gasoline engines like some large vehicles like tools like chainsaws and lawnmowers, small vehicles like mopeds, motorcycles, and outboard motors on boats. Now, certain low-income countries will actually have more 2-stroke and diesel engines than 4-stroke engines. So, like places like China and India might have quite a few bit more of the 2-stroke. Easier to make, but they have their own problems. So, like for example, in Shanghai, China, there was something like 1.2 million scooters. So, a lot easier to get around on a scooter than it is in a big car. Now, what is getting produced depends on the engine and the fuel combination. So, how the engine burns is going to produce different concentrations of NO and hydrocarbons and VOCs. There's no easy apples to apples comparison. You cannot compare a diesel engine to a 4-stroke to a 2-stroke because of this. Now, the size of the vehicles will vary, and some will have catalytic converters that will actually remove some of this pollutants prior to exhaust. So vehicles will rarely run under ideal conditions and controlled loads. So they're almost always going to be running hotter and dirtier than what you might get in a laboratory setting. But that does not make this impossible to study, just because they don't run under laboratory conditions in the real world. So the first thing we need to talk about is the Otto cycle, which is the basic 4-stroke engine. This is different from the well-known Carnot cycle, which is something that is used to study simple engines. But so, following this era of the ideal Otto, you have an intake stroke going from 1 to 2, where basically the pressure stays constant, but the volume expands. So, as we're looking down here, the intake stroke, the piston goes down, fuel comes in. But because the volume is expanding as the gas is going in, the pressure stays constant. Then we have a work stroke, the compression stroke, going from 2 to 3. So pressure builds up as the volume compresses. So this compresses to its greatest point so we can get the most amount of work. From 3 to 4, we combust, we burn it, we ignite the gas, which builds up temperature and pressure, but this is the magical point between picture 2 and picture 3. Our piston hasn't been allowed to move yet. But so we build up all this pressure, and then from step 4 to 5 at the power stroke, the gases expand, cooling and pushing down to reduce the pressure. And so this is where it gets the energy. It pushes the piston down. This is where we get our energy. And then finally, 5 to 6, we're fully pumping, pushing that up. We're pushing that up, and we're heat rejection. So we're allowing the gases to be released as the exhaust of the engine. So we're pushing the carbon dioxide and other things out, and water vapor out a secondary pipe. And then finally we can go back down to 1. So 5 to 6 and then back to 1 gets us back to the original spot, where we can then start to intake and start again. So the 4-stroke engine is this. So we have a separate intake and exhaust stroke. We have a compression and a power stroke. And so it has to complete revolutions as part of our cycle. Now, the efficiency of this cycle can be represented as following. The work, because this is a state function, the work and the heat must always sum up to a certain amount. We cannot get more energy than was in the gasoline. So, depending on the heat of this cycle, the heat lost, that's going to control how much work we can get out of this cycle. So one way to model this is looking at the difference between the T which would be the cold part of this cycle, 5, versus the T in the hot part of this cycle. The temperature differential on the engine is going to control how much work is possible. And it relates largely to the volumes and the compressions as well. But largely the engine has measured ratio of working. So as the alternative way is looking at compression ratios, but so the last statement saying that, oh hey, we could get more energy efficiency by compressing gases further. However, overcompression of gases can lead to premature combustion, which causes engine knocking, and then you lose some of the energy because you want it all to burn as one. You don't want it to like little firecrackers going off. You want one big explosion. But so if you could get the cold part of the cycle down to absolute zero, or like the hot part of the cycle to like melting like solar temperatures, you could have something like 100% efficiency. However, we cannot. And so oftentimes efficiency is close to like 40%. Now, one way to avoid premature combustion is to increase the octane rating. Largely speaking, straight chain hydrocarbons produce knocking at low compression. They will auto-ignite prior to having a spark. So if you just have one long hydrocarbon chain, it's easier for it to burn. Aromatic groups, so those rings with double bonds, or hydrocarbons with branches, meaning like it looks like a tree branch with the like limbs coming off of that, can be compressed to higher ratios without this pre-combustion. So when we look at an octane rating, the octane number is devised by a comparison to a mixture of N-heptane, which is just straight chain 7 carbon, versus something that's isooctane. So it's like so this would be 1, 2, 3, 4, 5 carbon chain with 2 carbons coming off as tails on each end, so it looks like a double fork. So an octane rating of 87 is a complex mixture that behaves equivalent to 87% isooctane and only 13% N-heptane. But rarely are we just mixing these two chemicals. So we're achieving this mixture with a variety of hydrocarbons, but it will behave similar to this mixture. We can increase the octane rating by adding more branched chains, more aromatic groups, or more aromatic-like compounds. We can also increase the ethanol rating, increase the octane rating by incorporating more ethanol or methyl tert butyl ether. We'll talk more about that in a minute. Now, the other way to increase the octane rating is by including a small number of appropriate additive. Back in the day, way before me, but we used to add tetraethyl lead. So a lead compound bound to 4 2-carbon groups was added to about 1 gram, a ratio of 1 gram per liter of gasoline to increase the octane rating. This was widely used as a fuel additive until 1975. It had its problems, but it's still used in some countries like Iraq and Yemen, and even Algeria only stopped using it in 2021. But this lead would react with halogenated compounds, which also added to the gas, to form lead halides, which was volatile enough to be emitted in the exhaust gas. So we used to have leaded gasoline. We stopped doing that because, it poisoned everyone. The gas in the exhaust is bad for your health. You're breathing in lead. The same reason we don't want lead in our water, lead in our paint, lead in our food is it causes lead poisoning, which also decreases our IQ and other things. But so lead in the gas, inhaled, is still bad. This would form an aerosol and settle on vegetation, increase in lead ingestion in the food chain. There are still some areas in the U.S. where along the roadways, there's still lead in the soil from this. But that's why we now use unleaded gasoline. It's called unleaded because we've ceased using lead. They used to charge a premium for, we improved the octane rating without the lead. So you paid extra to basically have the safer, greener alternative to your gasoline. But some people still refer to it as unleaded gasoline. That's why it's gasoline without our lead. Now, other ingredients include things like methyl cyclopentadienyl manganese tricarbonyl. That's a big mouthful. But cyclopentadienyl, that is a 5-membered ring with two alkenes, and we have two double bonds and methyl groups on it, so it's carbon groups, and that's bound to manganese, a metal, and 3 CO groups. This can be added at a much lower ratio. Now, while MMT is toxic, it does completely burn up in the engine, and only manganese oxides are the byproduct. So it's not toxic coming out of the engine. And while manganese is a nutrient in low doses, if we allow it to build up too high, it's toxic. So, thankfully, the amount used as a fuel additive is sufficiently low. We don't have to worry about manganese poisoning in our plants and food chain. Now, other such things we have to do is oxygenating additives. When we don't have enough oxygen to burn properly our fuel, we produce carbon monoxide, which is toxin, unburned volatile VOCs, so we give off some of the gasoline, and NO. Now, if we were to do a complete combustion of octane, it would take something like 12.5 oxygen molecules to completely combust octane into CO2 and water. So that's a ratio of mass of about 3.5 oxygens per weight of fuel, and would require something like 17 to 1 air to fuel ratio to achieve that, because remember, air is about like 20% oxygen. So if we do not get enough oxygen molecules, we get incomplete combustion, and so we get those byproducts. Now, even if we do complete combustion, we can still lose some VOCs from evaporation from the fuel tank or from the carburetor on hot days. They can just evaporate if you have incomplete seal on some of these things. So we can't avoid all of this, but we can try to minimize. And so one of the way we minimize this is by adding oxygenating compounds. Compounds that will increase the octane rating, but also add more sources of oxygen that will promote complete combustion of our fuel to get it to more CO2 and more water. One of our big ones that we used to use is methyl tertiary butyl ether, MTBE. This was useful because it was an industrial product based on a petrochemical feedstock. So methyl tertiary butyl ether. So it means tertiary butyl is a carbon attached to 3 other carbons. So it looks like a branch with like 3 legs coming, like a 3-corner stool. So 4 carbons all connected. 4 carbons with one of the 4 in the center. That's connected to an oxygen. The methyl is the single carbon on the other side. So it's a 5-carbon molecule with an oxygen in there. When added by about 15% by volume to the fuel, it was cost effective and increased combustion and the octane rating. Now, the problem was it was also incredibly stable when not under combustion conditions. So when you would have leakage of fuel, either old underground tanks of fuel would leak into the water supply. This is how they store the fuel in these at gas stations. They put in these large underground tanks. Well, when they leak, the oil wouldn't mix with the water, but the MTBE has the capacity to hydrogen bond with the water, and so it can dissolve into the water supply. So, and this is a carcinogen, and so it was stable enough that it would dissolve into the water supply and it wouldn't break down, and it would be a carcinogen, so it was hard to get rid of and caused cancer. So we've since banned in at least 25 states since 2007. I'd have to look and see. It's probably banned in more. Generally, we don't use this very much. Ethanol is the preferred version. Ethanol, of course, has its own drawbacks. Ethanol is more costly to produce. It cannot be shipped by pipeline, meaning, so like we cannot just put it in a thing and transport it by a pipe. Either it's, you can't put it as a gas very easily, and so we can't ship it long distances very easily. And we cannot store it with the gasoline. It needs to be blended near the retail outlets. Like, it will degrade over time. So we can't just put it in the gasoline and then ship it across the country. We have to transport it somewhere nearby, blend it, and then ship it to the gas stations. While ethanol will reduce the carbon monoxide emissions, it also increases the volatility of our gasoline by 7 kilopascals, measured as a Reid vapor pressure. But the 1990 Clean Air Act requires certain volatility ratings based on an area's climate. So, like, we have to account for certain things, especially like when it's hotter, more of it will evaporate. So we have to deal with that. But so while MTBE is produced industrially, ethanol is an agricultural product and thus a biofuel. So we can produce this from sugarcane, from maize. It's largely a renewable resource, but there are still some effects. The effects of devoting vast areas of farmland just to grow fuel for our vehicles means we aren't able to produce as much food. To grow higher yields, we use synthetic fertilizers. And the manufacture of these synthetic fertilizers also require fossil fuel, as well as other raw materials. So just because it is a biofuel, an agricultural byproduct, doesn't mean it's all good. We have to consider all the extra effort that goes into it. So we'll look at this real quick. A case study, an energy budget when using maize as a fuel source. So the process of making ethanol is 2 steps. We fermentation under conditions to enhance microbial reactions, and distillation to separate the alcohol from the other byproducts. The fermentation process is we convert essentially 3 equivalents of hydrocarbon, which is going to be our sugar, into 1 ethanol and 1 CO2. The byproducts will include milling waste that can be used as animal feedstock, but from distillation, the residue stillage can be used as feedstock for chemicals and animal feed or soil amendment. But so the energy output. Ethanol can produce 19 times 10 to the 6 joules, so 19 megajoules. And the co-products can produce something like 8.2 megajoules for a total of 27.2 megajoules. But the energy input, so like corn production, is 5.4 megajoules. And the processing is 9.1 megajoules. So a total energy input of 14.5 megajoules. So if we look at it from the energy input to energy output, it's only something like 88% efficient. However, if we take away the co-products of and don't include that, that's only 31% gain, 31% efficient for fuel gain. So energy efficiency is only considered significant if we include the byproducts as well. But while fuel-based energy increases CO2, while it does increase our fuel efficiency, it does also increase the CO2 production. Okay, we will stop there. But we will look at catalytic converters and other aspects when we get back on Wednesday.